Hello students, once again welcome to the LJ Institute of Engineering and Technology. Let's start with the course Mathematics 1. Today's chapter is Sequence and Series and today's topic is Monotonic and Bounded Sequence and Sandwich Theorem. In previous lecture we have seen the convergence of sequence. Now in this lecture we are gonna learn about the monotonic. What is monotonic sequence? What is bounded sequence? How we can find monotonic and bounded sequence, and by using this, how we can check the sequence is convergent. And we have one theorem is sandwich theorem. Okay, so let's have a look on first increasing sequence. What is increasing sequence? So a sequence un is called increasing if for all n greater or equal to 1, this un is less than un plus 1. N plus 1, un plus 1, that means next term of this un. As n increase, then next term goes to large and large and large. This is called increasing sequence. Increase term, each and every term is goes to increase as n increase. Okay, so we can say that this u1 is less than u2, like u2 is greater than u3 is greater than u2, u4 is greater than u3. Okay, so as n increase, term is also goes to large and large and large. Let's understand with one example. As n increase, we have term n square plus 1. If start with the 0, if we put n is equal to 0, so 0 plus 1 is 1. If we put 1, so 1 square plus 1 is 2. This is goes increasing. Okay. If we put here 2, so 2 square 4 plus 1 is 5. So as n increase, term increase, and it goes to this. So this series you can see by graph. This series goes to increase, increase, and increase. Okay. Here you can see increase. So this is a simple increasing sequence. Now what is the decreasing sequence? So a sequence un is called decreasing for all n greater or equal to 1. That means as n increase, then sequence decrease. That means un is greater than un plus 1. That means un plus 1 next term goes to smaller and smaller and smaller and smaller. Okay, that means this. The next term is smaller than this previous term. That u3 is smaller than u2, u4 is smaller than u3, u5 is smaller than u4, and so on. Let's have a look on the graph. So as n increase, graph is of 1 by n. You can see if we put starting from 1, so 1 gives 1 by 1 1. If we, n is equal to 2, next term n increase, answer will 1 by 2, that's 0.5. 3, 1 by 3, 0.3, 4, 1 by 4. That means as n increase, 1 by n goes to like this, starting from 1, 2, 3, we have 1, 1 by 2, 1 by 3, and so on. So it goes to smaller and smaller and smaller. So starting from here, 1, 1, then 1 by 2, 1.5, and 1 by 3, and so on up to this. As n tends to infinity, 1 by infinity goes to 0. This is decreasing. Okay, this is decreasing. And now sequence is called monotonic if it is either increasing or decreasing. So this increasing sequence and decreasing sequence, I have just taken two definitions because we want to understand what is monotonic. What is the word monotonic? Monotonic, that means if sequence either increasing or it is decreasing, then we can say that sequence is monotonic. If it is increasing, then monotonically increasing. If it is decreasing, then monotonically decreasing. Okay, so this is the definition. Now let's have a look on the example, and by example we will understand the increasing and decreasing or not. Okay, so prove that sequence this is decreasing. So here we have this sequence. This is our un. Now we have to prove that this sequence is decreasing. Decreasing, that means un is greater than un plus 1. We have to check this. That means as n increase, the term goes to decrease. Okay, so let's start with the un. First we have write down un. Then we will find un plus 1. So this n is replaced by n plus 1. So we have 3 by n plus 3. Now we know that, or it is clearly from here, this term is less than this term. Okay, it is clear now. N plus 2 is less than n plus 3. So n plus 2 is less than n plus 3. If we take a reciprocal of this, so this n plus 2 is become greater than this term. Okay, and if we multiply 3 on the both side, then there is no change. So this 3 is greater than this term. That means this un is greater than un plus 1, and by definition we can say that, okay, for all n, by definition we can say that given sequence is decreasing. That means given sequence is monotonic. Okay, we can say that. Okay, so let's understand with one more example. Prove that the sequence is increasing. Same step, same concept, but how we can check that it is increasing? That means un is less than un plus 1. We have to check this. Each and every time we cannot use that equality. So in this example, we will learn how we can check that this un is less than un plus 1. So let's write down un. So if we will find un plus 1 by putting n by n plus 1. So numerator n plus 1 whole square. This here n plus 1 whole square plus 1. So we have formula n plus 1 whole square is n square plus 2n plus 1. And again same n square plus 2n plus 1. But this plus 1. So this is plus 2. Now we will check this one. un plus 1 minus un. And if un plus 1 minus un is greater than 0, then what happened? This happened, and we can say that is increasing. So by taking LCM, multiplication of this denominator in the denominator, and this multiply with this numerator, and this multiply with here n square. By cancel out this term, and by cancel out this term, we have 2n square cancel out this term, and we have remaining is this, and you can see clearly for n greater equal to 1, this term is positive. That means un plus 1 minus un is greater than 0. If we take this minus on right side, so we can see un plus 1 is greater than un. That means next term is going to get greater and greater for all n. So given sequence is increasing. So this is the second method. In previous example we have seen, we have taken by normal inequality. And in this example we have checked this un plus 1 minus un. So this is the second method to check how we can decide the monotonic or not. Okay, so we have one more example. You can pause the video and you can calculate by yourself also. Okay, check. Prove that the sequence un is equal to n upon n square plus 1 is decreasing. So very first step is taking un. Now find un plus 1. So numerator n plus 1. Here n plus 1 whole square plus 1. So we have n square plus 1. Formula is n square plus 2n plus 1. Plus 1 gives 2. Now we will find that un plus 1 minus un. So this is un plus 1. This is un. By taking LCM, cross multiplication, by simplifying, we have this answer, and we can see that this numerator is negative. So this entire term is negative. So un plus 1 minus un is negative. That means less than 0. Taking this on the right side, we have un plus 1 less than un. That means it is given sequence is decreasing. Okay, so you have to check only this, that un plus 1 is less than un, that is decreasing. and if un plus 1 greater than un, then sequence is increasing. Okay, now we have second point of this topic or this lecture is bounded sequence. What is bounded sequence? Okay, so let's have a look on the basic concept. A sequence un is bounded above if there exists a number capital M such that this nth term un bounded by some particular number m, this m. All the term of un, that means for all n greater or equal to 1, all the term is less than this n. Then we can say that this sequence is bounded above by this n. Okay, and we have this example un is equal to this. If we start from the 1, if we put here n is equal to 1, so 5 minus 1 gives 4, 5 minus 2 is 3, 5 minus 3 is 2, 5 minus 4 is 1, 5 minus 5 is 0, 5 minus 6 is minus 1, minus 2, minus 3, minus 1, 2, minus infinity. Here maximum value of this is m, and all the raised terms are less than this 4. So this is our upper boundary. That means we can say that this is bounded above. This sequence is bounded above. Simple. By this m, and this m is your this 4. Okay? Understand? Now the sequence is bounded below if there exists a number m such that all term of the sequence is greater or equal to this m. This is the smallest value, and all other values of each and every term is greater than this m for all n greater or equal to 1. For example, un is equal to n. If we start from the 1, so 1, 2, 3 up to infinite. So this 1 is our lower boundary. Okay, this is our lower boundary. Lower than 1, we don't have any value because we are starting from the 1. So this is bounded below. This is called bounded below. Okay, now what is only bounded? That means if it is bounded above and below both, then we can say that un is bounded. If it is bounded above only, so we will use bounded above. It is bounded below, we can say that bounded below. And if it is bounded above and below both, then we can say that given sequence is bounded sequence. Okay, for that we have one example. So un is equal to 1 by n. If we put, we know that this sequence starting from the 1. So we start from the 1. So 1 by 1 is 1, then 1 by 2, 1 by 3, 1 by 4, 1 by 5, up to infinite. 1 by infinity is 0. And after 0, we don't have any term. So this is our lower boundary, this is our upper boundary. Lower and upper. Okay, maximum 1, minimum 0. This is our upper boundary, this is our lower boundary. And that's why we can say that this un lies between 0 and 1. And that's why we have bounded above upper boundary, bounded below 0 lower boundary, and that's why given sequence is bounded. Okay, this is the example of bounded sequence. It is bounded above and bounded below. So this is the concept of bounded sequence. Now we have one theorem, and theorem says that every bounded and monotonic, bounded we have seen, and also monotonic we know that if sequence is increasing or decreasing, we can say that is monotonic. So if any sequence is bounded and monotonic, it is convergent. So we have one more theorem for convergent. Okay, that was the concept from limit, and this is the concept from bounded and monotonic. Okay, so we have example based on this topic. Prove that sequence un is monotonic. That means either increasing or decreasing. And then check it is convergent or not. by using this theorem, just we have seen. So to check increasing or decreasing, as we have seen in this lecture, start with the un, and next we will find the value of un plus 1, then we will check un plus 1 minus un by taking LCM, by cross multiplication, by simplification. This term is positive, that means un plus 1 minus un is greater than 0. So if you take on the right side, so un plus 1 is greater than un, that means it is increasing, and increasing, that means it is monotonic. Now we have to check it is bounded or not. Okay, so it is bounded by this un, nth term is bounded by -1 to 1. We can check for all n greater or equal to 1. So by theorem it is bounded, and by theorem we can say that it is bounded and monotonic. So given sequence is convergent. Okay, this is the concept based on bounded and monotonic. Now we have one more example. So that sequence this un whose nth term is this. This is the nth term. Okay, this is the nth term of this sequence un is monotonic increasing. Now we have to just show this is monotonic increasing. That means we have to show as that un plus 1 is greater than un. And then check is it convergent. For that we have to check bounded or not. Okay, so we have un is this un plus 1, that means next step is u3n plus 1. Now we will check un plus 1 minus un. So all this term is minus, so cancel out with this. Remaining is this term, and this is positive for all n greater or equal to 1. So un plus 1 is greater than un, so we can say that it is monotonically increasing, or we can say that directly it is increasing, or we can say that it is monotonic. Now we have to check it is bounded or not. Okay, for that we have un is nth term. Now you can see here this is geometric series GP, which is already you have studied in school level. This is geometric in progression and with common ratio 1 by 3. Okay, and a is equal to 1. So we have formula a for finite series, a into 1 minus r raised to n upon 1 minus r. So a is 1, r is 1 by 3. So we put r raised to n is 1 by 3 raised to n. And this, by simplifying this, we have this. This is 3 by 2. We can take outside, and we have this bracket. Now it is clear that this term is less than 3 by 2. Why? Because this gonna infinity, okay, as n tends to infinity, this is x and x greater than 1, as we have discussed, we have seen in some standard limit. So this gonna as per, so this term is less than 3 by 2, so un is bounded above by 3 by 2. That means each and every term of un is less than 3 by 2, because this multiply with 3 by 2 here, that's why. So it is bounded and it is monotonic and bounded above, so we can say that by theorem series is convergent. Okay, now one more example. Prove that sequence an, where an, nth term is given by this, is convergent. Simple. Now you cannot solve this by that limit only. Okay, some limitation are there, so we will use this concept, increasing and bounded. So we have an is given, then find an plus 1, then an plus 1 minus an. So by cancelling out all this term, just cancel out, na? So we have this, and this is positivity itself. We can see clearly here positive. So an plus 1 is greater than, so it is clearly seen that it is increasing monotonically. Now we will check it is bounded or not, and if it is bounded, then we can say that it is convergent. So to check bounded, we will take this concept that 2 raised to n minus 1 is less than n factorial for all n greater or equal to u. You can check. Okay, why we have taken this? Because this is factorial. So we will convert this factorial series into some power, so we can apply here geometric progression. That's why. Okay. So by using this, let's put the value of 2. So 2 raised to 2 minus 1. 2 raised to 2 minus 1, that means 2 raised to 1, which is less equal to 2 factorial. It is clear. Okay. Similar way you can check. Now taking reciprocal, if we take reciprocal, so this inequality will be changed. Now we put n is equal to 2. So we have this, that means is factorial of this 1 by 2 factorial, 1 by 3 factorial, 1 by 4 factorial, and so on is less than, these are the less than 1 plus 1 by 2 raised to 1, 1 by 2 raised to 2, because we have this proved, and that means this is our geometric series. Okay, and we can apply for infinite term is a upon 1 minus r formula, sum of this series. Sum is given by this geometric. Okay, so this is a is equal to 1 and common ratio 1 by 2. So a 1 and 1 minus 1 by 2 gives 2. So this an is bounded by 0 and 2. This is bounded series, and we know that monotonic and bounded, that means it is convergent. Okay, so these are the concept of monotonic and bounded, and from monotonic and bounded we can check the convergent. Now we have last point, sandwich theorem. So it is also we have learned in school level. If we have this inequality and we know the limit of un and wn is equal to L, then we have the limit value of Vn is also L. Okay, so let's discuss the convergence of the sequence. This. Okay, now we want to discuss the convergence of this. That means we want to find the limit of this. As I told that the factorial, that means we cannot find the limit so directly. So we will find this limit by using the sandwich theorem. And if sandwich theorem, if we can find this limit value, then it is finite, that is convergent, it is infinite, then divergent. Simple. Okay, so first we have this un, and if we put 1, 2, 3 up to n term, we have 1. If we put n is equal to 1, so 1 factorial 1, 1 raised to 1 is 1. If we put 2, so 2 factorial divided by 2 raised to 2, this gives 1 into 2 and 2 into 2. If we put 3, so 3 factorial divided by 3 raised to, so 3 raised to 3, that means 1 into 2 into 3 divided by 3 into 3 into 3, 3 raised to 3. Okay, and up to nth term, so n factorial 1 into 2 into 3 up to n, and n into n into n into n, n times. Here we can write this nth term as this 1 by n into of this, and it is notice that here, notice that numerator is bracket numerator almost 1, because numerator is less than or equal to its denominator. Numerator is less than or equal to its denominator. So we can say that this un, that means this un is less than or equal to 1 by n. This un is less than equal to 1 by n. Now we have this inequality, so limit of this is 0 and limit of this as n tends to infinity, this is also 0. So by sandwich theorem we can say that limit of this un is also 0, which is finite, so it is convergent. Okay, so as we have discussed by sandwich theorem, limit of un is 0 and it is finite, so given sequence is convergent. So how we can use sandwich theorem to check the convergence? We have seen how monotonic help us, how bounded help us, and how sandwich theorem help us to check the convergence of sequence in this lecture. Okay, so we have one more example here. Discuss the convergence of sine n by n. That means u and n term is n by n. We have this. Now we know the one concept of sine, that sine lies between minus 1 to 1. The range of sine is minus 1 to 1. If we divide this by n, so we have this inequality. Now this is our 2 new sequence. We can find the limit of this boundary. So limit of this is 0, limit of this is 0. So both the value are same, 0 0. So we can say that limit of this un is also 0 by Sandwich theorem, and which is finite, and therefore by the definition of convergent it is convergent. Okay, so we have one more example. Discuss the convergence of cos square n by n. So we have un is equal to cos square n by n. Now as we have seen that range of sin x is minus 1 to 1, similarly cos x is what, it is cos square. So between 0 to 1 divided by n. Now find the limit of 0 is 0, find the limit of 1 by n as n tends to infinity is 0. So we have both the limit value is 0, so we have limit of this cos square n by n is also 0 by Sandwich theorem, and this is finite, so we can say that given sequence is convergent. Simple, so easy. Okay, this concept you know very well because we have studied in previous lecture. As I told, whenever you are starting with next lecture, you have to refer previous lecture and you have to practice this DIY. That means do it yourself. These are the practice example. In this example, you have to check that given sequence is monotonically increasing or decreasing, or it is bounded, and it is both, then it is convergent or not, that we have to check. So thank you for watching this video. Keep watching, keep practicing. We will see you soon with next lecture of series. Okay, so these are the 2 lecture of sequence. Now onward we are starting with the series. So thank you for watching this video. Thank you once again.